Okay, now we want to look at what happens if we have more than a single two category proportion. So the two categories like success and failure. So this is where this testing for goodness of fit using chi-square. Well, goodness of fit. It's a multiple proportion test. Okay, so let's go here and talk a little bit about it. Again, we have this is section 3.3, and this is the chi-square. Chi, that's a Greek letter, and then I square there. Chi-square goodness of fit. And so, let's just look at something really simple. Maybe it's not always just successes and failures, right? So your categories for something could be more than two things. So three or more categories within that categorical variable, and so you could look at anything like size, right? Small, medium, large. Okay, there are three categories that you may count and look at proportions. There could be something to do with speed, and you could just again have some three, say slow, medium, fast. But you could get into something like age, and you could have infant, toddler, preteen, maybe, I don't know, something like that. Teenager, or it might be adolescent, or something along those lines. You might have young adult, middle age, and so forth, right? So you could have all kinds of categories, but talk about the proportion of people or things that fit those ideas. So so that's all around us, and yet our success failure thing, that particular test, it was only good for success failure, only two categories, but now we have three, and so in looking at that, what might we have? Well, I'm going to take the book's example, and in their case, they have race as the different categories, and they're looking at jurors, race on a jury, and the question here is, is it representative of the bigger population? And yeah, that's usually a good question. We're supposed to have jury by peer. Well, peer could include things like socioeconomic status, racial group, ethnic group, gender, all sorts of things, and so it might be worth looking at, does a jury, the composition of the jury, reflect the composition of the community it's pulled from, right? Does it reflect the population? And so if we go take a look at their numbers, so they, this is the setup is, and while I talk about it, I'm writing it down on my stuff. So they have really 3 categories for race plus the other. They have these the races there, and they have the total number for the juries, and then they also have the percentage or the proportion from the registered voters. Okay, so that would be the hypothesized proportions. So what, 72%, 7%, 12%, and 9% for those. And now it is very key that those add up to 100% or 1 when you have that. So we'll go back over here. So I've written those down. Those were the voters. This was the juries. And so the question is no longer, so if I just had white and black, or black and Hispanic, or Hispanic and other, or black and other, or something like that, I could take those 2 categories and call them successes and failures. And again, success and failure is just which one are you truly counting and which one is the other. But here I have these 4 categories, and I would like to know, though, it's a hypothesis test of, do they reflect those numbers? Well, of course, the 275 sort of reflects the 100%, but do these, do the 205, 220, or the 26, 25, and so forth, 19 reflect those numbers? Well, on first look, actually, they look pretty good. In particular, looking at the smaller numbers, so the other is 19 out of 275. That's probably, I don't know, I'm not sure, maybe 6 or 8%, maybe. The 25 out of 275, that is, quit. I'm not sure why something's coming up there, but anyway. The 19 out of 275 is probably a little low. You would expect more like maybe 24 or so for other. Hispanic, 25 out of 275. That is 1/11th, and so that would be somewhere around 9%, and so that might be a little low. And again, the 26 blacks, that is a little less than 10% of the total, and yet they're 7%. So it looks like actually it probably is pretty representative. And so in this case, our research question, really could be, is it representative? I mean, that may be what we want to know, is this representative? Oops. Okay, that could actually be the real research question, but now framing it in a test of hypothesis, the question really is, so my H0 would be that the proportions, the jury proportions are, and I could go through, and say something like a P1 equals 0.72, P2 equals 0.07, P3 equals 0.10, and then what, P4 equals 0.09. The jury proportions are these, or come from a population with these, you know, that there's nothing weird going on here. Basically, you're asking, were they selected randomly? Okay, the jury proportions are this, and jury selected. Now, randomly is a kind of a weird word there, because there's no way they are truly selected randomly, but could they have had the same makeup as being selected randomly? And then the alternative would be that at least one proportion is different. Okay, so that's what we're trying to test. And now you could test, we can use this method to test just a success and failure. But the nice part about this method to get chi-square goodness of fit is it will expand to as many as you need. And okay, so we have that. Now, the way this method works is we have to produce, we have to create the hypothesized data, okay, or the null data. And the way we're going to do that is we're going to simply take the 275 times each of these population proportions. Okay, so let's see. I have to look at their answers. So we call these the expected counts, and here is where they have them. So I'm going to write those down. So I've got the actual data, the observed, and then we've got the expected. And so notice on the observed, the numbers are all what were there before out of the 275. And then when we multiply 275 times 0.72, we get 198. And when we multiply 275 times 0.07 or 7%, we get 19.25. And for these expected counts, even though we're counting people, it is absolutely fine to put in decimals and so forth. And then notice that when you add all those up, they will add up to the 275 jurors that we were looking at. Okay, and so coming back, there I have them. And again, this was white, black, Hispanic, and other, and then total. And so we look at that, and what we want to check is how much difference there is between each of these. And so the way this statistic works, we're going to come up with a chi-square statistic. And it's really still based on the normal distribution. And in this case, though, when we create this, we are looking at a difference. So notice we're going to take the observed, so 205 minus the 198. And again, that's the kind of thing we were doing before. We did it with proportions. We said we wanted the hypothesized, the data. So I've got that here as well. 205 is the data. So we took the data proportion minus the hypothesized proportion. Well, if I just put those over 275, they would be those proportions. Okay, so we don't worry about the fact we're not dividing by 275. And then we need that difference divided by a standard error. Well, actually, notice this says chi-square. So what this actually looks at is the square of a normal population. And so that's a statistical thing and so forth. But we would square that, and the way we're getting our standard error estimate is actually coming from the expected population, the expected number in the population. Now, again, the left side says chi-square. If I were to take the square root of this, right, I would get the difference, the 205 minus 98, over the square root of something that has to do with the standard error. And remember, in the proportion things we did earlier, to get the standard error, we needed a square root. Okay? And I am not going to go into how this chi-square statistic is mathematically equivalent to the pooled standard error and so forth, but it is. It turns out if I only had two categories here, I would be using actually the same data, same types of things in this chi-square that I would calculate for the single proportion test. So with that, we just add up all these, so the calculation is relatively simple if you had to do it by hand, but we don't want to do it by hand. So 19.5 or 25, square that, plus 25 minus 33 squared over 33, plus 19 minus 24.75 squared over 24.75. Okay, so that computes this chi-square, and then once we get that number, we would find a probability to get a p-value. Okay, use the chi-square distribution. Now, we do need to talk about degrees of freedom. I think that's good to understand that depending on how many proportions we have, you get a slightly different chi-square distribution, and so that's what the degrees of freedom are helping us with, is which is the right one. And so since there were 4 columns here, I need 3 chi-square distribution with 3 degrees of freedom. Now, you made a template in your project, or are making a template in your project that looks like this. And so what we need to put in here are the hypothesized probabilities. So those were 0.72, 0.7, no, sorry, 0.07, 0.12, 0.09, and then that was it, so I'll just get rid of that one. And down here we had 205, 26, 25, and 19. So that was our hypothesized distribution and all that. And so now here are our expected counts, and those do match what the book had. 198, 19.25, 33 and 24.75. And if I look over here to the right of my template, I see that these probabilities did sum to 1. That was 275, that's 275. And then here I calculate all those z-squared values and add them up, and I get 5.889. So there's my test statistic, 5.889 in this case, adding those four numbers. Degrees of freedom are 3, it automatically did that, and I get a p-value of 0.117. Okay, so p-value of 0.117. Okay, this becomes a p-value equals 0.117. And once again, this is big. Boy, all my data are bigger than 0.05. I don't know why. So we fail to reject H0. And so what that means is we fail to have evidence. We don't have evidence to say the jury proportions didn't come from the population. Okay? Right here, the alternative would be at least one proportion is different. In other words, at least one of those, in one of those columns, one of the columns, the observations didn't match the hypothesis in at least one of those columns. But we don't have evidence to say that that's the case. Okay? So we don't have evidence to claim the juries are different from the population. Okay. Now, again, this is one of those things. The p-value is 11%, so it was only 0.11. In other words, there was only an 11% chance of getting our particular kind of data if it did really, in fact, come from the population, which isn't really huge. So what it may say is you need more data. Maybe 275 is too small. Maybe it was twice that, it would be enough. And actually, you can kind of check that very quickly. If I just take 2 times each of these numbers, that will be twice the sample size, but the same relative proportions. So if I make that 410, and this one 52, and this one 50, and this one 38, I now have twice the sample size, and notice that those same proportions, so I have 550 now. Those same proportions, I just doubled the numbers, so everything's the same relative proportion it used to be. But now all of a sudden, I get a p-value of 0.008, which is definitely well under 0.05, and that would say, oh, there would be evidence here to say that these numbers, the 410, 52, 50, and 38, don't really reflect the population numbers of 72%, 7%, and so forth. So that it's very unlikely that these juries really represent the population. Okay? So sample size is a big key, is that even the tiniest differences, if I have a big enough sample, are significant. And so it kind of becomes, well, what's a reasonable size sample? And I don't know. 275 might have been a very reasonable size sample, and it failed to show a difference. But maybe it was too small. I don't know. I'd have to know more about the size of the county and all those different things to have an idea whether it seemed reasonable. But if it had been 550 or twice the sample size, we would have rejected the null hypothesis and therefore decided that indeed at least one of those counts here did not reflect the proportion up there. Okay, and so that is chi-square test of independence.